Let's look at another example. And now what we're going to do is we're going to prove some inequalities using induction. Again, we want to look at our basic induction method. So our basis step, we want to show the proposition is true for the smallest element in the set. Then we want to do our inductive step, and that's show that if the proposition is true for n equals k, then the proposition will be true for n equals k plus 1. So proving identities or inequalities requires us to string together inequalities in a particular order so that we can show that our proposition is true. It's a bit more difficult than proving identities. It's a little less straightforward, but it's not too terrible. All we've got to do is we've just got to kind of think to ourselves, well, how do I make the statement that one thing is greater than or less than another? So let's take a look at an example. Let's prove for n greater than or equal to 4 that n factorial is greater than or equal to 2 to the n. So we'll start with our basis step, and since we want to know n greater than or equal to 4, our basis step starts with p of 4. Okay, so we'll let n equal 4. 4 factorial, right, is going to equal 4 times 3 times 2 times 1, which equals 24. Okay, and 2 to the n, 2 to the 4th, is equal to 16. So that means 4 factorial is greater than or equal to 16, right? Thus we have proven, okay? Thus, P of 4 is true. Now we go on to our inductive step. Our inductive step now is we're gonna let for k greater than or equal to 4, k factorial is greater than or equal to 2 to the k. And so that's our basic assumption, right? We need that k is greater than or equal to 4. We started with 4. That's like the first step in our ladder. Now we're going to move up from there. This is our assumption. Now we're going to say, okay, k plus 1 factorial. Well, k plus 1 factorial is k factorial times k plus 1. And by assumption, that should be greater than or equal to k factorial, 2 to the k times k plus 1. So what you want to think is well, since k plus 1 is positive, because k is greater than or equal to 4, we're taking a positive number and we're multiplying it by a number that actually is less than our original value, so it should remain less. It should be the inequality should maintain or should hold. Okay? So now, here's the thinking here. If I think about this, k plus 1, well, first I want to look at 2 to the k plus 1 is simply equal to 2 to the k times 2. And the question is 2 to the k times k plus 1 greater than 2 to the k times 2? And the answer is absolutely yes. Okay? What we can say now is, we can say, well, 2 to the k times k plus 1 must be greater than or equal to 2 to the k times 4 plus 1, because k is greater than or equal to 4. Okay, which is necessarily greater than or equal to, in fact, strictly greater than, 2 to the k times 2. 2 to the k times 5 is bigger than 2 to the k times 2. You don't really need to do much proof work with that. You can just say that. We all agree. That's true. And so hence, and this is equal to 2 to the k plus 1. Thus, what we get here is we get k plus 1 factorial, which is what we started out with. This value right here is in fact greater than, strictly greater than actually, 2 to the k plus 1. Ta-da! And we're done. That's finished. So basically this thing here is just my thinking, how I'm thinking through things. Our proof just starts out with the k plus 1 factorial. I take k factorial, I'm going to separate out my k plus 1, put in my assumption, okay, and then I'm going to make the statement that it's greater than or equal to when I replace my assumption, okay, with my k factorial with the assumption. And then it's just a matter of figuring out which values are greater than or less than whatever. And it takes a little bit of logic, a little bit of thinking through. There's no real formula for doing it. But basically, if you kind of work through these things utilizing some either numbers or algebra, you should be able to figure out what values are greater than what values. And basically, that's what we're going to try and do. We're going to try and just string together these inequalities. It takes a little bit of thought, takes a little bit of practice. Let's take a look at another one. Let's prove for any non-negative integer n greater than or equal to 3 that 3 to the n is greater than or equal to n cubed. So I'm going to start out with my basis step. My basis step, non-negative integer n greater than or equal to 3. So I'm going to start with p of 3. And that is then 3 to the third, okay, which equals 81. All right. And then we get n cubed is 3 cubed. And that also equals 81. Well, those two are equal. So 3 to the third is, in fact, equal to 3 to the third. So p of 3 is true. Notice how we utilize the 4, like the n greater than or equal to 4 in the last problem. We're going to use this fact that n is greater than or equal to 3 later on in here. So you want to kind of be thinking to yourself, oh, remember that n is greater than or equal to 3 as I'm working. So 2, we've got 3 to the n plus 1, or 3 to the k plus, we're going to let 3 to the k be greater than or equal to k cubed. By assumption, so we'll take 3 to the k plus 1, and what I'm going to do is I know that that's going to equal 3 to the k times 3, which in fact is going to be greater than or equal to, and that's going to be k cubed, 3 times k cubed. Now what we're going to see is that we're going to see I've got 3k cubed, and so this is going to end up equaling k cubed plus k cubed plus k cubed. And there's a reason why I'm doing this, and that's because if I look here, I want to try and prove that this is in fact greater than k plus 1 cubed, which is equal to k cubed plus 3k squared plus 3k plus 1. Now, on the one hand, I have this k cubed statement. There's k cubed. And then I want to look, I've got 3k squared. Now, 3k squared is going to be less than, strictly less than k cubed if k is greater than 3. And since we're looking at numbers greater than 3, or it's going to be actually, it'll be less than or equal to k cubed if k is greater than or equal to 3. So we can actually do a direct substitution. We can kind of make this equal to, we're going to make it less. So it's going to be greater than or equal to k cubed plus, here's the 3k squared. Okay, there's that first term. Then we need now the 3k plus 1. Okay, well, k cubed, when is k cubed going to be greater than 3k plus 1? Well, it's going to be greater than 3k plus 1. Both are going to be positive. If I have, this is 3 cubed is 81. That's certainly greater than 3 times 3 plus 1, which is equal to 10. So in fact, we are now strictly greater than. We can actually remove this and make the 3k plus 1 right here. So what I did right here is to notice that I've got k cubed plus k cubed plus k cubed. I broke out 3k cubed. And when I did that, I kind of made an argument for each term. The k cubed matches. These two k cubes match. Fine. They're equal. 3k squared is going to equal k cubed, and in fact will be less than k cubed if k is greater than 3. So we can keep actually the equality there, but then 3k plus 1 is going to be strictly less than k cubed when k is greater than or equal to 3, and so hence we can just change this to strictly greater than. And so what we've done is we've shown that each term, one by one, is in fact less than. And this thing here is then equal to k plus 1 cubed. And there we are. That's done. Another alternative proof that we could use here, utilizing same logic, so we'll call this 2, is we've got k cubed. This is going to be strictly greater than k cubed plus 3k squared. We already have that one. Plus, and let's say plus 4k. Or 3 squared times k when k is greater than or equal to 3. Excuse me. And that's going to then be strictly greater than k cubed plus 3k squared plus 4k. because that's 9k. 9k is bigger than 4k, and k is positive. And this equals then k cubed plus 3k squared plus 3k plus k, right? Just using a little algebra. And this is then going to be strictly greater than k cubed plus 3k squared plus 3k plus 1. And we're done, okay? Which equals k plus 1 squared. So on the one hand, we could actually go term by term, making a comparison against the values in k plus 1 cubed when k is greater than or equal to 3. Or we have another one that's a little bit more algebraic, right? Basically where we kind of separate things out, still taking advantage of the fact that n is greater than or equal to 3. That's still a really important piece that we're going to need inside of this proof. So thus, what we get here is that this 3 to the k plus 1 is greater than or equal to k plus 1 cubed. And then therefore, by induction, for n greater than or equal to 3, 3 to the n is greater than or equal to n cubed. And we're finished. So again, we've got a pretty similar process here. We are still going in, we're pulling out one of the terms, and then substituting in for our assumption, just like we did before, but now we've got to actually like make some inequality judgments, or inequality, do some inequality work. And that's essentially what we've got going on here. Okay? In this case, we kind of went in and we proved that our k cubed, when we actually substituted in, was, when we broke it up, that term by term, each value was less than the original value that we were looking at. Okay? So I hope this helps to kind of give you, like, to spark some ideas as you're working through your induction.